Welcome to Frank Stajano Explains. Today's topic is exam question walkthrough. It's still exam season, and so once again I'll walk through an exam question in algorithms with you. But as I said other times, there's an important rule for making the most of exam questions, and it is to attempt it yourself as seriously as if you were in the exam before having a look at the solution or at a video like this, which describes a solution. So a reminder of my video with the recipe from my mentor Professor Mencuccini over there, and pause this video. Here's the question over here, and I'll see you when you have solved it yourself. Give yourself half an hour and then restart once you're ready to talk about it with me. Stop the video, I mean it. All right, welcome back. And so let's have a look at this question. Part A, consider the radix sort algorithm. Explain how radix sort works, blah, blah, blah. Explain why running radix sort does not proceed from most to the significant digit. Give a proof by induction of the correctness, blah, blah. All this stuff is essentially bookwork or bookwork plus epsilon, and so there's no point discussing it. Just go ahead and read it. It's the kind of part of exam question which is an easy lead-in, kind of free marks, which you would only get if this were a closed book exam, as it was when this was set. In an open book context, you would never get this type of easy stuff. It's about saying, well, do you remember this stuff, and did you understand it well enough that you can explain it again, including all the nitty-gritty detail and maybe some slight variations. But okay, with open book it would be trivial, so you wouldn't be getting any of this if you are in an open book setting. Now let's get on with the meat of the stuff, which is part B for 7 marks. What are we being asked to do in part B? Clearly describe an algorithm strictly better than big O of n squared that takes a positive integer s and a set A of n positive integers and returns a boolean answer to the question whether there exist 2 distinct elements of A whose sum is exactly s. Evaluate its complexity. All right, well, that doesn't look too bad, maybe. I think that for things to add up to s, there has to be a big one and a small one, or maybe a slightly bigger one, a slightly smaller one, unless in the limit there's 2 that are the same. But anyway, it would do me some good perhaps to sort these numbers and start from the 2 ends. So if I did that, I would line up these numbers, sort them, which of course will cost me big O of n log n, just for the sort. But it's still less than n squared, so I might still be able to get away with that. And then I start from here. Well, actually, I shouldn't start from here. I should start from something that is at most s. Well, actually, if strictly positive integers means that 0 is not in the set A. There's a debate whether 0 is positive or not. But anyway, let's say that positive is strictly positive. So if 0 is not in the set, then s will never lead to 2 numbers adding up to s. So I should start from s minus 1. So I go here until I find s minus 1, until I find something that's strictly smaller than s. And from then on I say, all right, now let's see, who can I pair this up with? Maybe this one, maybe this one, maybe this one. Well, there's only one number that will work with this one, and it's the complement to s of this number. So this number is strictly smaller than s. If I say s minus this number, then where is it? And I could look for it in here. But if I don't find it, I have to find the next smallest number here from the big ones, and then look for its complement in here. If I don't find it, still the next one. So this looks suspiciously like a quadratic search. I've already paid this stuff for sorting them, and then I'm doing this thing for each one of them. I'm potentially looking up all the other ones from the bottom. So it looks like ultimately I'm not I'm not doing any better in asymptotic terms than if I had just stupidly brute force through all the possible pairs. I just get myself the Cartesian product of A with itself, and I take all the pairs, and for each pair I see if the numbers add up to S or not, which costs big O of n squared. And this strategy that I was working towards ends up being no better than that in asymptotic terms, and so that's not so good. If I were slightly smarter in looking for the complement, so I'm trying this one and see if I can find the complement to S in here. Since I have paid to sort them, I don't have to go in order. I could actually do some kind of binary search in here to find the complement to S, to find if it's there or if it's not there. So if it's there, I find it not in linear time, but in log n time. And if it's not there, then I have to try with the next one, and I search for its complement in log n time and so on. So I would pay n times for this loop that tries the big one, and within each loop a smaller loop of log n cost for finding its complement. So I would end up paying n log n for this search, which is the same as this, which is good because it means I have now a total cost of n log n, which is strictly better than big O of n squared. So I have answered the question satisfactorily. And I could be satisfied with that. However, when I think slightly harder about this problem, I may have another idea. I had another idea, which is, why do I need sorting them in the first place? Sometimes, instead of order, chaos serves me better. And if I just don't bother sorting them, but I stick them in a hash table, then with the hash table, I can query in constant time whether they're there or not. So sticking each of the numbers unsorted in the hash table costs me just big O of n. Okay. Inserting each number in the hash table. Each number goes in at constant cost, so total big O of n. In fact, if I want to optimize while I'm at it, I should just not even bother inserting the numbers that are S or greater, because I know that they will never form a valid pair. So after I've done this first linear pass, I look at all the keys that are in the hash table, and for each key I say, well, this is the key. Is the complement in the hash table, which is test I can do in constant time again. So with another linear pass, I do a constant time test for each number until I find one that matches, and at that point I have returned my answer in 2 times linear, which is still linear time. Wow, that's a lot better than this n square that I was supposed to do better than, and even of the n log n that I did earlier. So I should be pretty pleased with myself. If I think about this slightly harder, then I notice some subtleties that if, for example, the number is, let's say S is 10 for the sake of argument, and I hit upon 5, then 5 is in the hash table, and the complement of 5 is 5, and then 5 is in the hash table, and I would say yes, but the question said whether there exist 2 distinct elements of A, so 5 and 5. It would work if there were 2 copies of 5, 2 or more copies of 5 in my set A, but I can't really tell if I use this process. And in fact, the hash table, there's another thing that I have overlooked, which is when I stick things in the hash table, this is all well and good if they were all distinct in the first place, but nobody told me that the set A of n positive integers were n distinct positive integers. There could be duplicates. So maybe I should refine my technique to cater for those 2 points, and say when I insert a number in the hash table, I should make the key the number, but the value in the hash table, which I was ignoring previously, the value should be the count of how many times that particular number appears in A. So the first time I insert in the hash table, it would be set to 1. If I insert another number in the hash table and I see that that key was already in there, so I should do the test before, I should increment that count that I already have for the number instead of just overwriting. So I end up, after the first linear pass, with set of keys which are the distinct elements in A, and for each one I say how many copies of them are present in A. Good. So at that point, when I check for, when I do my second linear pass and I take a number and I say, what is its complement? Okay, if the complement is itself, then I know it will be there, obviously, but I should only say yes, Boolean answer true, if the count of that key is at least 2. And if it's just 1, I should say no, because I wouldn't be able to produce 2 distinct elements of A, whose sum is exactly S. And that way, I have solved my special cases too, and I should be very proud, and definitely be earning my full 7 marks for having found a solution of complexity very strictly better than big O of n squared, namely big O of n. Very happy. If you're also happy, stick a like on this video. See you.